What up, y'all? We're back. We are testing out this mechanism of me being able to do videos quickly without having to spend a ton of time editing. I am going to move on to lesson 3, problem 8, where we're going to be graphing an exponential function. Here, we're going to combine our use of pen and paper analysis with some online graphing functionality, maybe through desmos.com, to get a nice graph of what this looks like. Specifically, let's go ahead and start with some sample points. So suppose that we start with like, I don't know, x equal 1. So, or maybe x equal 2 would be kind of nice. So what we'll say is we're going to try to evaluate the function f of x equals 2 to the x. And we'll start with x equal 2. So we'll go ahead and say let f of x equal 2 to the x. Based on our previous discussion, I want to kind of call out two nice features of this function. The first feature that's kind of useful is that the thing on the bottom, we call that the base, is constant. So this is going to be constant base, and the value of that base in this case is 2. And then this thing up top, we're going to say that this is a variable exponent. And remember, when we have a constant base and a variable exponent, we're going to call that an exponential function. So we're going to say that this function 2 to the x is called an exponential function with base 2. That's how we say that. And I like to write that. Let's write this in English. So f of x, sorry. Let's write the entire statement out in English. This is called figuring out how to say this stuff out loud. F of x equals 2 to the exponent x. So that's one way to say that. We could expound a little bit more and say the function f of x has a constant base 2 and a variable exponent value given by input x. This is an exponential function. It's kind of the definition of an exponential function, that the base is constant and the exponent is variable. Remember that power functions have the reverse. In a power function, the base is variable and the power, the thing in the superscript, is going to be constant. All right, let's go ahead and sample. So we're going to start with the value x equal 2 for our input. And we'll consider what happens when we evaluate at f of 2. So in this case, we're going to call this 2 to the x power, and we'll go ahead and use this kind of interesting evaluation bar. This is notation that is particularly kind of relevant later in our careers in calculus. So what this basically says, this little straight line that's kind of long says, take whatever is over here, and everywhere you see an x, substitute in the value x equal 2. So that notation is called evaluation bar. And we'll see that kind of later in our lives as well, perhaps, if we're lucky. So everywhere we see an x, we're going to evaluate 2. So this is 2 squared. We remember that 2 squared is going to be 2 times 2. Today happens to be a Tuesday, so I believe it's the case that 2 times 2 is actually 4. So we'll say that f of 2 is equal to 4. Which means I can go back to this table of values, and for the input 2, I'm going to say that the output is 4. This time, let's go ahead and graph that ordered pair 2, 4 immediately. So we'll go along the x values. Remember, the x values are the inputs. We'll start at 0 and we'll go +1, +2. Positive is in the right direction. And then we'll go up to 4. Notice that each 1 tick mark is actually a half because 2 tick marks makes 1. So at 2, we're going to go 1, 2, 3, 4. I feel like I would have done better to actually include right tick marks on that. Next time I'm going to do that. So I'll go ahead and say that that is 4. All right. So now we've got this f of 2 is 4. We'll box that to make it super easy for us to come back and look at it in the future. Let's go on to the next one. So let's go 1 down. Let's go to x equal 3. So we'll say let x equal 3. And we'll find f of 3, which is going to be 2 to the x evaluated at x equal 3. So let me go ahead and write that out in English. This math is 2 to the exponent x evaluated at x equals 3. Remember, we called that thing the evaluation bar. And then what we're going to do here is actually, everywhere we see an x, we're going to evaluate and substitute in the value of 3. So this is going to be 2 to the third. I'm not sure if that 3 is super easy to read. Let me make that a little bit bigger here. And then remember that if I take 2 to the third power, that means multiply base 2 by itself, where the base shows up the number of times in the exponent. So that's 2 times 2 times 2. 2 times 2 is indeed 8, which we could have written as 4 times 2. And another way to say that that's 4 times 2 is that this is actually 2 squared times 2 to the first, right? Because there's 3 of them. So here there's 2 of them. There's 1 of them. The reason that that's kind of useful, we'll see in a second. This is pattern recognition, and I'm kind of just prepping us to remember our rules of exponents. So f of 3, which is 2 to the third, we've just discovered that that is indeed 8. So we'll go ahead and box that to make it super clear what we're looking at. We'll go back to the table of values, and we'll put in 8 here. And then let's go ahead and graph the ordered pair 3, 8. So I guess one thing that is kind of useful to recognize is that everywhere we have an input output pair, that is recognized as what we call an ordered pair. So this is what we call an ordered pair. And then the left coordinate of that ordered pair we call the input, the right coordinate we call the output. And then some people like to call that the x value and the y value. We'll capture that in just a minute. So over here, when we're graphing, we go over to the input value, which is the x value of 3, produces output value 8. So here we go, 1, 2, this is going to really bother me. Sorry about this. I actually create these little things for myself, and I am not impressed with my tick marks this time because I can't actually read on the right-hand side what the values are. So I'm just going to go ahead and fix that on my own paper. For those of you that had to follow along at home, lo siento mucho, porque ya tienen que hacer más trabajo. Okay. For those of you that grew up speaking Spanish, I am always jealous, playfully jealous, because that is one of my dreams, to speak Spanish as if I grew up with it. Okay, so here we go. We go all the way up to 8 in this situation. And that now represents the point 3, 8. Let's do another one of those. So I'm going to go ahead and draw a horizontal line to say that work belongs up there and the work that I do below belongs below. And in this case, we'll go down to the next value of x. We'll call that x equal 4. and we'll find f of 4. Suppose if we were really excited about this, we could use the evaluation bar once again. So we'll say that this is 2 to the x, but in this case, we're going to let the value of x be 4. So let's go ahead and write that. Everywhere we see an x, we're going to substitute in 4. So that's 2 to the 4th power. And then remember, a rookie mathematician will do all their math over to the side, run out of space, and make a dumb error because we can't even read our own writing. Professional mathematician is going to run out of room and say to themselves, let me get another piece of paper, right? So let's be, like Ludacris said, the great philosopher, too many rookies, not enough pros, right? So let's be a pro here. So here we go. We're going to grab this thing, and we'll say that this is 2 times 2 times 2 times 2. Which of course is going to be, well, do you notice something here? Here are 3 2's, and then this is just one more 2. And the reason that I write it like that is we just saw what 3 2's multiplied to. 3 2's multiply to 8. So this is going to be 8 times 2. And 8 times 2 is, of course, 16. The reason that that's kind of useful is here's 3 2's. So we're going to look at that as, remember that exponents count multiplication. So here we've got 2 to the 3, and then here's 1 2. And if you notice, this is going to be 2 to the 3 plus 1, which we just said was 2 to the 3 times 2 to the 1. That's actually kind of an algebraic property of exponents. When we multiply two exponents with the same base, we can sum the exponent values. So 3 plus 1 is indeed 4. Here we get that this is 16, which immediately says that f of 4, we're going to call 2 to the 4th, to the value of 4 in the exponent, or the exponent value of 4. We said that that was 16. Let's go ahead and capture that in a box. I got my value in a box there, right? So when we are looking at this thing, we put 4 there, and then this is going to be 16. So remember that when we write it in this form, we're going to call that an ordered pair. And in this case, the input value is going to be known as the x value. That's on the left coordinate. So this is the left coordinate. So the left coordinate actually stores the input value. If the one on the left is called the left coordinate, we might call this one the right coordinate. And we'll call that the output y value. Okay. So now that we have the 4, 16, we can go back to our original table and put in 16 here. And let's go ahead and put in 4. So 4 goes up to 16. We're starting to see a pattern. I don't know if you want to do one more for giggles. I always like to do at least 4 when I'm doing this work. And so maybe we just do one more, and then we start to see if we can evince or guess the pattern. And then once we've guessed the pattern, we'll use a calculator to confirm our guess. So let's go ahead and look at the last one here, which is 2 to the 5th. So we'll do one more here, and we'll say x equal 5, and we'll evaluate f of 5, which is going to be the function 2 to the x evaluated at x equal 5 using the evaluation bar, which of course is 2 to the 5th. Well, remember that exponentiation, when I have a 5 in the top, that's literally just going to be the base b, or in this case base 2, multiplied by itself so that there are 5 copies in that product. So here I've got 1, 2, 3, 4, 5. Now, of course, we could actually do all those multiplications out. One of the principles of good math is work really, really hard at the beginning and then leverage your hard work in your future. So specifically, we already know what 2 times 2 times 2 times 2 is. because indeed 2 times 2 times 2 times 2 is 16. We literally just did that. So this is now 16 times 2. 16 times 2 is a much easier problem. In fact, we are now to the place where I am running out of room. As the great philosopher Ludicrous says, too many rookies, not enough pros. When a rookie mathematician runs out of room, he does all his math on the bottom and messes up because he can't even read his own handwriting. When a pro mathematician runs out of room, she grabs another piece of paper and literally just continues on. So 16 times 2 is going to be 32. I do want to kind of note that 16 is actually going to be 2 to the 4th times 2 to the 1. And then, of course, we say that 2 to the 4 plus 1, 4 plus 1 is 5. But indeed, these things are kind of breaking up. I can actually split addition in the exponent into multiplication of the bases with the summands on either exponent value. What we just saw there was that f of 5 is equal to 2 to the 5, which is 32. And that is equivalent to the ordered pair 5, comma 32. We've already kind of seen that we're not going to be able to graph that on the axis that our teacher provided for us because it's not large enough in the y component. Just for good form, we're going to remind ourselves that this is called an ordered pair. And perhaps we develop even more sophistication with our nerdy language. We'll call that the first coordinate, and we'll call this the second coordinate. A lot of different ways to say the same thing, which is sometimes helpful. All right. Now I think I'm ready to start asking myself the question, what patterns do I see? And I like to actually make this an explicit part of my math practice. All right, so let's go ahead and just kind of look back over what we've just seen here. So specifically, we saw that each time we took the next value of x, so we went from 4 to 5, we literally took the previous output and just multiplied by 2. So each time we take the next integer value of x, we take the output of the previous integer x value and multiply by 2. Let's go ahead and confirm that this conjecture actually works. And to confirm that that conjecture actually works, let's go back to the actual table of values. So we started at x equal 2, that was 4. When I go down to the next integer value, that's 2 goes up to 3. And what I did is I literally just took the last one and multiplied by 2. 4 times 2 is 8. Okay, we go down to the next integer value. Sorry, I forgot to fill that in after we did that evaluation. So we literally just evaluated 2 to the 5th as 32. I just forgot to write it there. Okay, so let's go down. When we go from 3 to 4, 3 down to 4, so x equals 3 down to x equals 4, I take the last integer value, that's going to be 8, multiply by 2, which is 16. I go down to 4 to 5, I take 16, I multiply by 2. If this pattern holds, then I would take 32 and multiply by 2, which is 64. Next question is, well, why does that make sense? Remember that we're taking 2 to the x. So 2 to the 5th is going to be 2 times 2 times 2 times 2 times 2, 5 times. When I go to 2 to the 6th, well, I have 5 copies of 2, then I just multiply by 1 more. So whatever the 5 copies of 2 were, I multiply that by 2 and I get down to the one below it. So of course that makes sense based on the definition of this exponential function. The next thing that I'll say is, okay, so when we're filling out this table, one of the things that we notice is to get from one line of the table down to the line below it, we actually just multiply the last line by 2. So from 4 to 8, I multiply by 2. 8 to 16, I multiply by 2. 16 to 32, I multiply by 2. So in the downward direction, we multiply by 2. To move down from one row to the next, we multiply previous output by 2. So that's the observation or the pattern that we're noticing. Well, if moving down requires multiplication by 2, could you guess what moving up requires? Yeah, you probably get it. What's the opposite? So moving down means multiplication. Moving up is the opposite. What's the opposite of multiplication? Yeah, division. So specifically, to move up a row, divide last output by 2. So specifically, to go from 64 to 32, 64 divided by 32 is, 64 divided by 2 is 32. 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2, well, that would be 1/2. Now, I'm not ready to go to a place where we try to figure out what 1/2 divided by 2 is. And in fact, we can kind of do that. So we just noticed a pattern. To go down, we multiply. To go up, we divide. The last thing that we're going to do here is to figure out what we just said. So notice we have this pattern, 2 to the 1. Well, that's one copy of 2, which is just 2. 2 to the 0, we've said that if it follows this pattern, 2 to the 0 has to be 1. 2 to the -1 would be 1 divided by 2, which is just 1 divided by 2, which we could rewrite as 1 divided by 2 to the first. And then the next question that we had, well, what was 2 to the -2? Well, we said it's going to be the last one, which is 1/2, divided by the one before it, or excuse me, divided by 2. We could write, suppose we could do this on a different line. So let's go ahead and write this as 1/2 divided by 2/1. Remember, if I take a fraction a divided by b, and I divide that by another fraction d divided by c, that's equivalent by doing a divided by b times d over c. In other words, we take the right fraction and we turn it into what we call the reciprocal. So in this case, we're going to flip it and reverse it, which is Miss Elliott's claim. In this case, 1/2 times 1/2 is going to be 1 times 1 over 2 times 2, which we could actually write as 1 divided by 2 squared. And of course, 1 divided by 2 squared is 1/4. Notice that the negative exponent turned into a positive in the denominator. What we just saw is that this is 1 divided by 4. We could guess, well, if this is 1/2, 1/4, if we do the same technique again, we might say, well, this thing is going to be 1 divided by 2 to the third, which is going to be 1/8. And then this is going to be 1/16. I encourage you all watchers that are following along at home to not trust me. I'm lying through my teeth, and I am not to be trusted until you confirm for yourself. So I'm going to go ahead and graph all these things. And then we've got this really, really interesting function that's called an exponential function. I really like it when my bank account looks like this, although I tend to believe that the assumption of exponential growth comes from an economy that is based on colonialization and slave labor, which makes me very, very angry. But anyways, the point of this thing is called an exponential function, right? We've kind of got that behavior. Let's go ahead and confirm. We'll go back to desmos.com. So let me just show you how to get there. We'll leave this page, so desmos.com, and then we'll go the graphing calculator way. And then what we're going to do is we're going to do the add item button. We'll go down to a table. We'll say that this is X, and we'll call the output to, I always forget how to do this. I think it's shift. Yeah, so shift 6 gives me an exponent. And then notice we want to fill out the table for these values. So I type in -4. Oh, I think Jaden's calling. What up, Jaden? Can you hear me? Hello, hello? Jaden, can you hear me? Okay, so if I just keep going here, 1, 2, 3, 4. Notice that I get this really, really nice behavior. I could click on this thing and go over here. I can increase the points of the size of the points. I can change the color of those. Sugar. We'll push done. And then here, if I type in 2 shift 6x, I get this very, very nice function, which looks identical to the function that I've graphed. And that is how we graph an exponential function given by 2 to the x. Thanks so much for your attention. Hopefully we can come back and finish up the other parts of this problem in another video. Bye, y'all.